Unit 6, pages 179 to 187. Riemann sums, a graphical approach to approximating the definite integral. In calculus, the result of the integral of f of x dx is a function that represents the antiderivative of the function f of x. This is also sometimes referred to as an indefinite integral. It's called indefinite because on our integral sign there are no values indicated specifically that we're looking for. The result of the integral from a to b of f of x dx is a value that represents the area of the region bounded by the curve of f of x and the x-axis on the interval from a to b. Calculating Riemann sums is a way to estimate the area under the curve, the value of the integral from a to b of f of x dx, for a graph function on a particular interval. In this activity, you will learn to calculate 3 types of Riemann sums: left hand, right hand, and midpoint. And also, some of you will learn trapezoidal sums. So we're going to do a few approximations together, and you've been assigned the approximations that you specifically are going to work on. The first approximation is a left-hand Riemann sum with the intervals of length 2 units. So let's consider for a moment the function f of x is equal to negative 1/3 x squared plus 2x plus 5. This function is graphed below. On the interval from 1 to 7, subdivide the area bounded by the graph of the function and the x-axis into rectangles of length 2 units. Place the upper left-hand vertex of the rectangle on the curve each time. Then calculate the area of each rectangle and sum of the areas to approximate the area of the region under the curve bounded by the function f of x from x equals 1 to x equals 7 and the x-axis. So we are looking for the area between x equals 1, x equals 7, the x-axis, and the curve of this graph. Okay, so we are basically going to find that area in there. So the way that we're going to do this is we're going to, like it says, we're going to create rectangles of length 2 units with the upper left-hand vertex of the rectangle on the curve. So every 2 units, so from 1 to 3, I'm going to have this rectangle where my vertex is going to be on the curve, and I'm going to create a rectangle. Okay, so this is going to happen every 2 units. So now from 3 to 5, I'm going to create a rectangle where the left hand of my vertex is on the curve. And from 5 to 7, again, left hand of my rectangle on the curve. So now I have these 3 rectangles, which I'm going to use to estimate the area under the curve of this graph. So if I remember, the area of a rectangle is equal to base times height. Okay, so in this case, the base of all of my rectangles is 2, because all of my rectangles had a length of 2 units. However, the height of all of my rectangles are different. So for example, the height of this first rectangle is going to be whatever value this point is, which is going to be f of 1, since 1 is the x value of this point. The height of my second rectangle will be whatever value this point is. So that'll be f of 3 in this case. And then the height of my third rectangle will be whatever value this point is, which will be f of 5. So what this means is that the definite integral from 1 to 7 of f of x dx is equal to, well, approximately equal to, my first rectangle, well, the area of my first rectangle, which is 2 times f of 1, plus the area of my second rectangle, which is 2 times f of 3, plus the area of my third rectangle, which is 2 times f of 5. Okay, so this, I can simplify this since every value is being multiplied by 2. I can bring that 2 out, and I have f of 1 plus f of 3 plus f of 5. And since my function is already given to me, all I need to know is what f of 1, f of 3, and f of 5 are, add them together and multiply by 2, and we get approximately 42.66. Okay, so that's the approximate area under the curve when my rectangles have a length of 2 units. Okay, so for approximation 2 and 3, depending on which one you have, right, you're either looking at a length of 1 unit or a length of half a unit. Okay, so depending on which approximation you've been assigned, determine the area under the curve for your units. Now we're going to change things up a bit. On our next 3 approximations, we're going to do a right-hand sum. That is, draw your rectangle so the upper right-hand vertex of the rectangle is on the curve of the function. So again, we're looking for the interval from 1 to 7 of the curve and the x-axis. So we're looking in this red area here, what the area would be. So we are going to create, again, rectangles of length 2 units. So now I want the right-hand vertex to be on the curve. So if I'm going from 1 to 3, the right-hand vertex should be on the curve. Right? So from 3 to 5, the right-hand vertex should be on the curve. And from 5 to 7, again, right-hand vertex should be on the curve. Okay. So once again, we're looking at the area of these rectangles. The base of my rectangles are all 2. Because my length of my units is equal to 2. All right, and now the height of my first rectangle is equal to the point that's on the curve, right? The vertex that's on the curve, which is equal to f of 3. And the height of my second rectangle is, again, the vertex that's on the curve, which is f of 5. And then last but not least, the height of my third rectangle is equal to the vertex that's on our curve, which is f of 7. So our definite integral from 1 to 7 of f of x t of x is approximately equal to 2 times f of 3 plus 2 times f of 5 plus 2 times f of 7, right? Which we can rewrite, since they're all being multiplied by 2, as 2 times f of 3 plus f of 5 plus f of 7, which is approximately equal to 34.667. Right? So you've either been assigned approximation 5 or 6. If you've been assigned approximation 5, you're looking at lengths of 1 unit. If you've been assigned approximation 6, you're looking at lengths of half a unit. Okay. Complete your approximation using a right-handed Riemann sum, where the right vertex of your rectangle is touching the curve. Okay. This question on page 182, these two questions, we're actually going to continue in class tomorrow with your groups. So don't worry about answering the inference question on this side of approximation 6. We'll work on that tomorrow in your groups. So now we're going to look at a midpoint Riemann sum. Midpoint Riemann sum is fairly similar to the right and the left hand. You're still creating rectangles. Now the difference is that the midpoint of your rectangle is the point that's going to be on the curve, right? So the midpoint will be the point on the curve. So again, we're looking at 2 units from the intervals 1 to 7. The x-axis and the graph are my top and bottom, and we're restricting it between 1 and 7. Okay, so now the midpoint Riemann sum, when you draw it, can be a bit tricky, right? So since our intervals are again 2 units, right? I'm looking for the midpoint of these 2 units. So from 1 to 3, the middle point is 2. So 2 will be the point that is on my actual curve. And from 2, I'll draw a line through, and that'll be my first rectangle. Okay, I'm actually going to do that in a different color for you so that you can see a little clearer. So 2 is my midpoint. I'm drawing my rectangle at that point. Right? Another 2 units over, we have 3 and 5. The midpoint of 3 and 5 is 4. So 4 is the point that'll be on my graph. And between 5 and 7, the midpoint is 6. So 6 will be the point that is on my graph. Okay, so now I have these 3 rectangles. And again, the base of these rectangles is equal to 2, since my units was 2, right? And the height of my rectangle now, of my first rectangle, is, since I used 2 as my midpoint, the height is going to be equal to f of 2. And the height of my second rectangle will be equal to f of 4. And the height of my third rectangle will be equal to f of 6. So now, the definite interval from 1 to 7 of f of x dx is approximately equal to 2 times f of 2 plus 2 times f of 4 plus 2 times f of 6, which we can rewrite as 2 times f of 2 plus f of 4 plus f of 6. okay, which is approximately equal to 40.667. Okay, so if you've been assigned approximation 8, you are going to look at lengths of 1 unit. Okay, so between 1 and 2, halfway in between would be 1.5. That is the point that you need to put on the graph. Okay, just keep in mind that we are still using the very same function that we started this problem with. The function is negative 1/3 x squared plus 2x plus 5. So if you need to identify the value, use that function. Okay. So now we're going to look at the last type of Riemann sum that we would be using. Okay, so on the next two approximations, we are going to draw trapezoids between the curve and the x-axis and approximate the area. Remember that the area of a trapezoid is found using the formula A equals 1/2 h times b1 plus b2, where b1 and b2 are the parallel sides and h is the distance between those parallel sides. Okay, so we're going to do a trapezoidal Riemann sum with the intervals of length 2 units. So on the interval from 1 to 7, so again, we're 1 to 7, we're bounded by the graph of the function and the x-axis. We want to draw trapezoids of height 2 units. Okay, so trapezoids come in many different shapes, right? We're used to seeing them look like this. In our case, our trapezoids are going to be flipped. So our trapezoids are going to have a situation that looks similar to this, or something similar to this. Okay, so the rules for a trapezoid are that they have 2 sides that are parallel and 4 total sides, period. That is a trapezoid. Okay, so we are going to draw trapezoids that are length 2 units apart. So we're going to have from 1 to 3, we're going to draw a trapezoid where the point of f of 1 and the point of f of 3 are both included in our trapezoid. So we're going to have a trapezoid that sort of looks like this. Let me actually use a different color so you can see the contrast, right? So we're going to have that end right, so there's our first trapezoid. Okay, so the whole point of trapezoidal Riemann sum is that the 2 endpoints of your length are both included on the actual curve. Okay, so for our next trapezoid, we're going from 3 to 5. So the point f of 3 and the point f of 5 are both going to be included. Okay. And then from 5 to 7, so f of 5 and f of 7 are both included. All right. So reminding ourselves that the area of a trapezoid is equal to 1/2 height times base 1 plus base 2. Right? And looking at our sketches on the side here, our height will be the bottom, and our base 1, base 2, doesn't really matter which one you consider to be which, are our 2 parallel sides. Okay, so if we look at trapezoid number 1, right, we're looking at the definite integral of f of x dx approximately equal to. So for trapezoid number 1, the area of that will be 1/2. Our height, which is 2, and our base 1, which we'll consider to be f of 1, plus our base 2, which was f of 3. Plus, again, we have a height of 2, so 1/2 times 2. Our base 1 is f of 3, plus our base 2, which is f of 5, plus trapezoid number 3, 1/2, again, a height of 2. Base 1 is f of 5, base 2 is f of 7. We can simplify this a bit because we're looking at 1/2 times 2 every single time. We can pull that out. So 1/2 times 2 of f of 1 plus f of 2, oops, not 2, f of 3, plus f of 3 plus f of 5 plus f of 5 plus f of 7. We can simplify this even more because 1/2 times 2 is just 1. So then we have f of 1 plus, and we have 2 f of 2's, so 2 f of 3 plus and 2 f of 5's plus f of 7. And this is approximately equal to 38.667. All right, trapezoidal Riemann sum is a tad bit trickier. You do have to pay attention to every single trapezoid separately, or else you might get confused. Okay, so if you do have approximation number 10, please make sure you are being accurate and you are taking your time when you are creating your trapezoids and finding the areas of them. All right, the last thing that you are going to do is you are going to enter your numerical approximations on the following page. So I'm going to enter the numerical approximations that we did together, right? So we did approximation number 1, we did approximation number 4, we did 7, and we did 9. Right, so for approximation number 1, we had 42.667. For 4, we had 34.667. For 7, we had 40.667. And for 9, we had 38.667. Okay, so these are all approximations for the same area. Let's remember that we're looking at the same area on the same interval for the same function, right? So these are all various approximations that we found for the 4 that we did together. After you've found all of the Riemann sums that you've been assigned, please also enter them on this page so that you are prepared for class tomorrow. Okay? You do not have to do the over and under approximation piece of this quite yet, and you can hold off on this piece on the right because later on when we do our next lesson, then we will actually work on that piece. Okay? The last page of this is actually going to be the next part of the classwork tomorrow, so you also do not have to work on this page either. We will look at that more tomorrow.